Design of experiments. Design of experiments, or DOE, is a structured statistical approach used to plan, conduct, analyze, and interpret controlled tests. The goal is to evaluate which factors might influence a process or a product outcome. DOE is widely used in engineering, manufacturing, and scientific research. It helps us understand cause and effect relationships, so we can pinpoint which input variables, or factors, have the greatest impact on results. By using DOE, we can identify key variables, understand how they interact, and optimize processes efficiently, often with fewer trials than traditional testing methods. This leads to better decision-making, higher quality, and reduced waste. In Six Sigma, design of experiments, DOE, plays a vital role, especially in the improved phase of the DMA methodology. First, DOE helps us identify the critical X's. These are the key input variables that significantly affect the Y, or the process output. Understanding these relationships is essential to improving performance. Second, DOE allows us to test hypotheses that were developed during the analyze phase. Rather than relying on assumptions or guesswork, we use structured experiments to validate which factors truly influence the outcome. It also enables faster and more reliable improvements. Because DOE is a data-driven method, it reduces the need for time-consuming trial-and-error approaches. Finally, DOE provides quantified insights, helping teams make evidence-based decisions. This leads to optimized processes, increased efficiency, and measurable gains in quality. This slide compares design of experiments, DOE, specifically factorial designs, with traditional testing, also known as OFAT, or one factor at a time. Starting with efficiency, DOE is much more efficient because it allows us to study multiple factors simultaneously. OFAT, on the other hand, changes only one factor at a time, which takes more effort and resources. When it comes to factor interactions, DOE shines because it can detect how different variables interact with each other. OFAT cannot detect these interactions, which means you might miss critical insights. In terms of time, DOE actually takes less time overall, despite testing more combinations, because it's strategically planned. OFAT may seem simple, but it ends up consuming more time because of its sequential nature. Lastly, data richness is another major advantage of DOE. It provides highly detailed, comprehensive data, while OFAT gives limited insight due to its narrow scope. In short, DOE offers more value, deeper insights, and greater efficiency, making it the preferred choice in Six Sigma and modern process improvement. Let's go over some of the key concepts in design of experiments, or DOE, that are essential to understand how experiments are structured and analyzed. First, we have the factor. A factor is a variable that we intentionally change during the experiment. For example, it could be something like temperature, pressure, or speed. Anything we believe might influence the outcome. Next is the level. This refers to the specific settings or values that a factor can take. For instance, if temperature is the factor, its levels could be high and low. These levels define how the factor is tested in the experiment. Then there's the response variable. This is the outcome or result we are measuring. It's what we're trying to optimize or improve, such as product strength, defect rate, or cycle time. Lastly, we have interaction. This is when two or more factors work together in a way that affects the outcome differently than if each factor was acting alone. DOE helps us detect these interactions, which is one of its biggest strengths compared to simpler testing methods. Together, these concepts help us design efficient, insightful experiments that can lead to real improvements in processes or products. This slide shows the step-by-step roadmap for planning a design of experiments, DOE. Each step is crucial to ensure that the experiment is well-structured and gives meaningful results. 1. Define objective. The first step is to clearly define what we want to achieve. Are we trying to optimize a process or solve a specific problem? Having a clear objective helps guide the entire experiment. 2. Select response variable. Next, we decide what outcome or result we'll measure. This is the response variable, and it should be directly related to our goal, such as quality, speed, or efficiency. 3. Identify factors and levels. Here, we choose the input variables, factors that we think may influence the response, and we determine their levels, e.g., high-low settings. Choose experimental design. Based on the number of factors and levels, we choose the right design, such as full factorial or fractional factorial, to efficiently explore combinations. 5. Run experiment. Once the design is set, we conduct the experiment by following the planned runs and collecting the response data accurately. 6. Analyze results. After the experiment, we analyze the data to identify which factors had significant effects and whether there were any interactions between them. 7. Optimize and confirm. Finally, we use the results to find the best settings for the factors and then confirm these findings with additional testing or validation. By following this structured roadmap, we ensure our experiment leads to actionable, data-driven improvements. This slide outlines the different types of experimental designs commonly used in design of experiments, DOE, along with their purpose and who typically uses them: green belts, GB, or black belts, BB. Full factorial design, 2 to the power of k. This is the most comprehensive design, where we test all possible combinations of factors and levels. It provides detailed insights and is suitable for both green belts and black belts. Fractional factorial design. When testing all combinations is too costly or time-consuming, we use a subset of combinations. This helps in identifying main effects and is primarily used by black belts. Randomized block design. This design helps in minimizing the impact of nuisance variables, those we can't control, but that might influence the outcome. It's an advanced technique, mainly used by black belts. Taguchi designs. These focus on robust design. The goal is to make the product or process insensitive to variation. It's a practical method that improves quality and is also used by black belts. Response surface design, RSM. This is used for process optimization, when we want to fine-tune variables to reach the best possible outcome. It's a sophisticated tool typically handled by black belts. This slide explains the concept of a 2 to the power of k full factorial design, one of the most fundamental experimental designs in DOE. We begin by exploring all combinations of k factors, with each factor tested at 2 levels, commonly high and low. The notation 2 to the power of k represents the total number of combinations or runs. For example, if we have 2 factors, A and B, each with 2 levels, the total runs would be 2 squared equals 4. The example table here shows how these combinations play out in an actual experiment. In run 1, both A and B are at low, and the output is 85. In run 2, A is at low and B is at high, and the output is 90. In run 3, A is at high and B is at low, and the output is 80. In run 4, both A and B are at high, and the output is 95. 2. A is high, B is low, and the output is 89. In run 3, A is low, B is high, and the output is 83. In run 4, both A and B are at high, and the output is 91. By testing all combinations, A full factorial design lets us study not just the individual effects of each factor, but also their interaction effects, which is extremely valuable for optimization and deeper insight. This method is powerful, especially in the early stages of process development or troubleshooting, as it provides a complete picture of how factors influence the response. Let's start with the main effects plot. This plot visually shows the individual impact of each factor on the response variable. When you see a steep slope in this plot, it means that the factor has a strong effect on the outcome. A flat line, on the other hand, suggests little to no effect. Next, we have the interaction plot. This plot helps us understand how the effect of one factor changes depending on the level of another factor. If the lines in this plot are parallel, it means there is little or no interaction between the factors. But if the lines are non-parallel or cross each other, it indicates a significant interaction effect, meaning the factors influence each other's impact on the response. Understanding these plots is crucial because they help us identify which factors are most important and how they work together, guiding us towards better process optimization. When conducting a design of experiments, there are some key assumptions we need to keep in mind. First, the factors we test should be independent of each other. Second, the measurement system must be stable and consistent throughout the experiment to ensure reliable data. Third, the errors or deviations in our results should follow a normal distribution. Finally, the variance of these errors should remain constant across all factor levels, a property known as homoscedasticity. Once the experiment is complete, we analyze the results using ANOVA, which stands for Analysis of Variance. ANOVA helps us identify which factors have a significant effect on the response. It also tells us whether interactions between factors are important. Additionally, ANOVA provides a measure of how well our model fits the data, typically expressed as R² or R². Understanding these assumptions and the role of ANOVA is crucial for drawing valid conclusions from our experiments and for optimizing the process effectively. When we have many factors to test, running a full factorial experiment can become very expensive and time-consuming because the total number of runs grows exponentially. To manage this, we use a fractional factorial design, which means we run only a fraction of the full set of experiments, like half 1/2, a quarter, 1/4, or even less. The trade-off here is that while we save a lot of time and resources, we get less detailed information about interaction effects between factors. Despite this, fractional designs are very useful in early stages, or when resources are limited. Let's talk about resolution levels, which help us understand how clearly we can interpret the effects in a fractional factorial design. Resolution 3 designs ensure that main effects are not confounded with other main effects. However, they can be confounded with two-factor interactions. So, while we can estimate main effects, we need to be cautious because interactions might be mixed in. Resolution 4 is a step up. Here, main effects are not confounded with two-factor interactions, but two-factor interactions might still be confounded with each other. This gives us more clarity when interpreting main effects. Resolution V designs are even better. In these, main effects and two-factor interactions are both clearly separated. That's why Resolution 5 is generally preferred for black belt level projects, where deeper analysis and precision are expected. Higher resolution gives more reliable insights, but it often requires more runs, so it's always a balance between accuracy and efficiency. Welcome to the Introduction to Taguchi Design. This methodology was developed by Junichi Taguchi, whose picture is shown here on the slide. Taguchi's approach is particularly focused on achieving robust design, which aims to minimize variation in a product or process caused by external or environmental factors, what we call Noise factors. In this context, we differentiate between two types of factors. Control factors. These are variables we, as users or engineers, can manipulate or set. Noise factors. These are elements outside our control but still impact performance. For example, environmental changes or usage conditions. A key concept in Taguchi design is the signal-to-noise SN ratio. This ratio helps us measure quality by maximizing the desired signal, i.e., performance, while minimizing variability due to noise. The table here highlights the three main SN formulas used in Taguchi methods. Larger, the better. Suitable when we want to maximize output. Think of product strength or battery life. Smaller the better. Ideal when we aim to reduce undesirable outputs, such as defects or emissions. Nominal is best. Used when precision around a target value is critical, like in dimensional accuracy. This foundation helps us make designs more robust and processes more reliable even in the presence of uncontrollable factors. Let's now talk about Taguchi orthogonal arrays and response surface methodology, or RSM. Taguchi orthogonal arrays are efficient, pre-planned experimental designs, such as L4, L8, or L16, that help us test multiple factors using fewer experimental runs. For example, an L8 array allows us to analyze 7 different factors using only 8 runs, which makes it extremely efficient and cost-effective in experimental design. Moving to the second part of the slide, what is RSM? RSM, or Response Surface Methodology, is a statistical tool used to model and optimize responses when we expect nonlinear relationships between variables. This is especially useful at the black belt BB level, where we're dealing with complex process behaviors. As shown in the 3D plots on the right, these curved surfaces represent how different input factors interact to influence the response. For example, in Graph A, we can see how the ratio of water to fruit powder and the extraction temperature affect the yield. Graphs B and C show other combinations of variables, all highlighting how response surfaces can guide us to the optimal set of conditions. In summary, while Taguchi helps us screen and plan efficiently, RSM allows us to fine-tune and optimize when relationships are not straight lines but curves, which is often the case in real-world processes. Now let's look at some common designs used under Response Surface Methodology, or RSM. Two widely used designs are Central Composite Design, CCD, Box-Banken Design, BBD. These designs are used when our objective is to go beyond simple linear models and fit a second-order or quadratic model. This allows us to explore curvature in the response, which is especially useful when we are trying to optimize a process. Using these designs, we can generate contour plots and 3D response surfaces. These visual tools help us understand how the factors influence the response and where the optimal region lies. Overall, RSM helps us fine-tune processes and make data-driven decisions when we're close to optimization. Let's look at two real-world case studies, one from manufacturing and one from a service environment, to see how DOE can drive impactful results. First, the manufacturing case study. The objective here was to optimize die pressure and temperature to improve product quality. After running a designed experiment and analyzing the results, the team achieved an 18% reduction in defects and a 10% reduction in cycle time. This not only improved quality, but also boosted overall efficiency. Now, the service case study. The focus in this case was to reduce customer wait time in a call center. The team looked at two main factors, agent skill level and tool speed, with the output being average wait time. By optimizing these factors, the result was a 22% improvement in customer satisfaction. These examples highlight how DOE can be successfully applied in both manufacturing and service sectors to improve performance, reduce waste, and enhance the customer experience. While design of experiments is a powerful tool, there are some common mistakes that can reduce its effectiveness if we're not careful. The first is ignoring factor interactions. Sometimes we focus only on individual factors, but interactions between them can have a major impact on the outcome. Overlooking these can lead to incorrect conclusions. Second, lack of randomization is a big issue. If we don't randomize the order of our runs, external influences like temperature, humidity, or operator variability might bias the results. Another common pitfall is using a poor measurement system. If the tools or methods we use to measure outputs are inconsistent or inaccurate, the data we collect won't be reliable, no matter how well the experiment is designed. Lastly, selecting the wrong type of experimental design, for example, using a full factorial when a fractional design would be more efficient, or vice versa, can lead to wasted resources and missed insights. By being aware of these pitfalls and avoiding them, we can ensure our DOE efforts lead to meaningful and trustworthy results. Let's quickly recap the key takeaways from what we've learned about design of experiments. First, DOE is a critical tool for validating solutions. It helps us move beyond assumptions and make decisions based on data. When you have a small number of factors, a full factorial design is a great choice because it lets you study all possible combinations and interactions in detail. If the goal is to design a robust system that performs well under a variety of conditions, Taguchi methods are highly effective. They focus on minimizing variation and improving consistency. And when your process shows signs of curvature or nonlinear behavior, response surface methodology, RSM, is the way to go. It helps you build a quadratic model and identify the optimal operating region. In the next steps, think about how you can apply these concepts in your own projects. Consider the complexity of your process, the resources available, and the level of precision you need. That will guide you in selecting the right experimental design.